We've already talked about how a benzene ring is very, let me draw a better looking benzene ring than that a benzene ring is very stable because it's aromatic. That these electrons in these pi orbitals that form these double bonds, they're actually just not in this double bond. They can keep swapping. This one can go here, this one can go there, that one can go there. Actually, they don't go back and forth. They actually just completely go around the entire ring. And when a molecule is aromatic, it stabilizes it. But we've seen examples of aromatic, or actually in particular, we've seen examples of benzene rings that have other things bumping off of them, whether they're halides or whether they're OH groups. And what we want to do in this video is think about how that might happen. How do things get added on to a benzene ring? So we're going to learn about electrophilic aromatic substitution. Let me write that down. Electrophilic aromatic substitution. And you might say, well, Sal, you just said you're adding things to the ring. But the reality is that there's 6 hydrogens here. There's 1 hydrogen, 2 hydrogens, 3 hydrogens, 4 hydrogens, 5 hydrogens, and 6 hydrogens. They're always there. If you don't draw them, they are implicitly there. So what we're actually doing, when you add a chlorine or a bromine or an OH group, it's actually replacing one of these hydrogens. That's why it is substitution. It's aromatic because we're dealing with benzene ring. We're dealing with an aromatic molecule. And we're going to see that we need a really strong electrophile in order to do this. So let's think about this, how this will happen. Before I do that, let me just copy and paste this because I don't want to have to redraw this. So let me just copy it just like that. So let's say we have a really strong electrophile. And I'll give you particular cases in the next few videos so you can better visualize what a really strong electrophile is. But just from the word itself, electrophile, you could imagine it's something that loves electrons. It wants electrons really, 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 really badly. And usually it has a positive charge. So it wants electrons badly. Wants electrons. Actually, let me make it very clear. Instead of saying wants electrons badly, because when you're talking about electrophiles or nucleophiles, you're actually talking about how good something is reacting. You're not actually talking about the actual energies involved. So let me put it a different way. Good at getting electrons. Good at getting electrons. Really, 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 really good at getting electrons. So what would happen? Well, we already said that this is already pretty stable. These guys, these electrons, these pi electrons can circulate all around. But if it bumps just in the right way to something that's really good at getting electrons, what might happen? Let's say we have this electron right here. That the way we've drawn it, it's on this carbon right here. Obviously, the carbon is just at the intersection. I never drew the carbon. But if this electrophile, which is really good at getting electrons, bumps in just the right way, this electron can go to that electrophile. That electron can go to that electrophile, and then would be left with. So let me copy and paste our original molecule. So then what would we be left with? So we no longer have this bond right here. It has now been bonded to the electrophile. Let me make it clear. We had this electron right here. That electron is still on this carbon right over here at this intersection. But the other end of it, the other electron, has now been given to the electrophile, the thing that's good at getting them. So the other side has been given to this electrophile. This electrophile now gained an electron, so it had a positive charge. Now it will be neutral. And once again, I'll show you several particular cases of this in the next few videos. And let me just make it clear. So this bond, you can now view it as being this bond. Now, this carbon right over here, this lost an electron. So if it lost an electron, it will now have a positive charge. Now, this is hard to do to a resonance stabilized molecule to a benzene ring. So that once again, and I said it, I'm being a little bit repetitive, this has to be a very good electrophile to do it. But once this is there, this is actually a relatively stable carbocation. And the reason why it is, it's only a secondary carbocation, but it's actually a resonance stabilized carbocation. Because this guy can go, this electron right here can be given to that. So if this electron goes there, then it would look like this. Let me redraw it. I'll draw the resonance structures quickly. So you have your hydrogen, you have your electrophile, that's what's not electrophile anymore, but you have that E that's now been added. You have that hydrogen, you have a double bond here. Let me make that draw a little bit neater. You have this hydrogen, you have this hydrogen, this hydrogen, and this hydrogen. And what I said is this is stabilized. So an electron here can actually jump over here. And then, so if this electron jumps over here, the double bond is now over there. If that goes over there like that, the double bond is now over here. Now this guy lost his electron, and it would have a positive charge. And then that is resonance stabilized. It can either go back to this guy, or this electron over here can jump over there. So let me redraw the whole thing over again. Redraw the whole thing. Let me draw all the hydrogens. So this right here, you have the E and the hydrogen. You have a hydrogen here, hydrogen here, hydrogen here, hydrogen here. And normally you don't worry about the hydrogens, but one of the hydrogens is going to be nabbed later on in this mechanism. So I want to draw the hydrogens just so you know that they are there. But as I said, this is resonance stabilized if this electron right here jumps over there, then this double bond is now this double bond. And now this guy over here lost an electron, so it would have a positive charge. And again, once you had this double bond up here, this double bond up there is that double bond. So we can go back and forth between these. The electrons are just swishing around the ring. So it's not going to be maybe as great as the situation that we had when we had a nice benzene ring that was completely aromatic. The electrons could just go around the p orbitals, round and round the ring, stabilize the structure. But this is still a relatively stable carbocation because the electrons can move around. You can kind of view it as a positive charge that gets dispersed between this carbon, and that carbon over there. Now, as I said, this is still not a great situation. It wants to the molecule wants to go back to being aromatic, wants to go to that really stable state. And the way it can go back to that really stable state is somehow an electron can be added to this thing. And the way that an electron can be added to this thing is if we have some base flying around, and that base nabs this proton right here that's on the same carbon as where the electrophile is attached. So if this base nabs a proton, so it just nabs the hydrogen nucleus, then that electron that the hydrogen had, let me do that in a different color, I reused. That electron that the hydrogen had, right over there, could then be returned to this carbon up there. And maybe that makes it a little confusing when I cross lines. It can be returned to that carbon right there. So what would it look like after that? After that, it would look like this. So let me draw so if that happened, we do it in yellow. We have our 6-carbon ring. 6-carbon ring. Let me draw all the hydrogens. So what did I do that in? That looks like a slightly green color I did that in. So I have all the hydrogens on that ring, all of the hydrogens. Now I have to be careful. This hydrogen right there, just the nucleus of it got nabbed by this base. So that hydrogen has now been nabbed by the base. If you view this electron right here has now been given to this hydrogen. So that electron has now been given to this hydrogen. And then the other electron in the pair is still with the base. The other electron is still with the base. So now this is the conjugate acid of the base. It has gained a proton. And on this carbon right here, we just have what was the electrophile. We just have what was the electrophile. And I'll do the same colors just to make it clear. What was the electrophile right over there? This bond is this bond. And then finally, we had, and I'll color code it here just to make clear, we had this double bond here, which is this double bond right over here. We had this double bond, we had this double bond, which is that double bond there, and this electron gets returned to this top carbon right here. So that electron, let me make it very, very clear. So the bond and that electron are returned to that top carbon. So then we have the bond and that electron returned to that top carbon. That top carbon is now going to be neutral. And once again, we are resonance stabilized. Oh, and one thing I forgot, just to make the charge stabilize, maybe this base had a negative charge to begin with. It didn't have to. But if this base did have a negative charge to begin with, it now gave an electron. It gave an electron to the hydrogen, so it is now neutral. And this should make sense, because before we had a plus charge and a negative charge, and then when everything reacted, everything is neutral again. The total net charge is 0. But this is the electrophilic aromatic substitution. We substituted one of the hydrogens. We substituted this hydrogen right here with this electrophile, or what was previously electrophile, but then once it got an electron, it's just kind of a group that is now on the benzene ring. And by going through this little convoluted process, we finally got to another aromatic molecule that now has this E group on it. In the next video, I'll show you this with particular examples of electrophiles and bases.